Welcome to today's lesson on calorimetry and measuring enthalpy of reactions. So we're going to start off by talking about what the concept and process of calorimetry is and how we use calorimetry, and then we'll talk about the calculations involved once we have set up the experiment and used calorimetry for our experiment. So calorimetry is the measure of heat changes during a process. And these processes can be chemical or physical. In order to focus in on the process that we're interested in, we need what we call an isolated system. And this is going to be a system in which no mass or energy is exchanged. And one of the important aspects of that is that the delta Q, the change in the energy inside the isolated system, is going to be equal to zero. And this is essentially the first law of thermodynamics, which we'll get to in a moment. So here's an image of three different systems. In system number one, or system A, this is an open system. In an open system, mass can be exchanged through the water vapor coming in or out, and energy can also be exchanged. In the second system is called a closed system because now with the stopper in there, mass can no longer be exchanged, but heat or energy can still be exchanged because the system is not thermally isolated. And then finally, in the ideal situation, in an isolated system, we have nothing being exchanged. And that means that everything should be contained within the system, within that container, and we'll be able to measure different aspects of what's going on inside that system. So the first law of thermodynamics, let me get rid of those underlines. I meant to do that before I started. The first law of thermodynamics essentially says that when you have two systems coming to an energy equilibrium, so some equilibrium in which some sort of energy is exchanged, two systems in energy equilibrium, the total energy is conserved. So like we said up above, the change in Q, that heat that's being exchanged, this is just the same Q that we saw way back when we did our lab on specific heat, and we'll actually be talking about specific heat a little bit today. When two systems come to equilibrium, there should be no change in the total energy within the system. And so if we label our two systems Q1 and Q2, or the energy coming out of or into the two systems Q1 and Q2, we'll see that Q1 has to equal the negative of Q2, which means that as one goes up, as one gains energy, the other has to lose energy, or the other way around. So what we're going to do in calorimetry is we're basically going to use water to act as a surroundings, because the water can absorb or release lots of energy without changing state, which makes it perfect. It has a very high specific heat, as you'll recall. And what we're going to do is measure a temperature change, that delta T, to first determine the amount of energy that's absorbed or released by the water. Now remember, the water is the surroundings, and so we'll tie that into the system in a little bit. Going back to the specific heat lab, you'll remember that the Q of the water, Q is equal to the mass of the water, and let's see if I can write the subscripts in there, times the specific heat, C of the water, times the delta T of the water. And just remember, Q equals MC delta T is what is listed on your reference pack. and that the specific heat of the water was 4.184 joules per gram times degrees C. That's always going to be the case in calorimetry, and that number is on your reference sheet. You don't have to remember it, but I'm sure that you will use it. Sometimes that degrees C gets listed as a Kelvin because Kelvin and degrees C have the same size unit. So 4.184 joules per gram times K can also show up sometimes. So don't be fooled by that. Don't try to convert between Kelvin and delta T and Celsius and delta T though. So delta T is the same in degrees C or Kelvin. Okay, don't add 273 to a delta T because the delta T is going to be the same. So the whole idea in calorimetry is that we're going to be measuring the heat of the water, and that the heat gained by the one system must equal the amount of heat lost by the second system. And so in a chemical reaction, system 1 can be the reaction and system 2 can be the water. It doesn't matter which one you call 1 or 2. And so if we add them all up, the Q of the reaction plus the Q of the water equals 0. So Q of the water, or Q of the reaction, has to equal the negative of the Q of the water that is in the calorimeter. And that's going to be crucial to understanding the calculations down below. Now, in order to perform calorimetry, if you'll recall, when we did our specific heat lab, we used styrofoam cups. And so I've got a diagram of a pretty good calorimeter to the right here. The calorimeter to the right is 2 styrofoam cups, and we have them inside one another because the air inside here is a good insulator. And we're going to call that an isolated system. So as we saw above, isolated system, nothing should be getting in and out. And so we should have a delta Q overall equal to 0. And the calorimeters are going to be assumed to be perfectly insulating. Where there's no heat lost or gained by interaction with the outside world. And we'll see in our lab that this may or may not be a good assumption. So once we've got our calorimeter set up, by the way, air is a good insulator. Vacuum is better insulator. And vacuum is a really good insulator. And so if you have a thermos, or you have one of those popular, which I do, the Hydro Flask, these both have vacuums inside them, and so they really insulate what's inside very well, and they prevent it from getting hot or cold, which is pretty cool. All right, so calculations, we're going to have to do a couple of calculations here, because what we're going to do is have some sort of a process take place inside our calorimeter, and then we're going to use Q equals MC delta T for the water. This is only going to be for the water, not going to be for the system, because the system is going to be a process which has an enthalpy. And what we're doing is we're going towards calculating the enthalpy of the process based on the Q of the water. And we're also going to have a delta T in which we have a final minus an initial temperature. And now, unlike before, we are going to pay attention to the sign of the delta T of the water, because if we don't pay attention to the sign, we might get our exothermic and endothermic mixed up when we go to calculate the delta H of the process. So in this case, I'm going to take 4.9 grams of, in example 1, of pure H2SO4. So we'll call this a gas. H2SO4 is a gas. And we're going to add that H2SO4 to 175 grams of water. Now notice we've got 2 masses here. You have to be careful to make sure you separate what the mass of the water is and what the mass of the reactant is. So this is the mass of the water. And here we've got the reactant. We're going to use that mass in a few minutes in a different way from the mass of the water. And they're both at 10 degrees Celsius. and the temperature of the water rises to 14.0 degrees Celsius, assuming the specific heat of the solution. So when we mix it together, we make a solution. We're going to always assume that the specific heat of the solution is the same as the water. Unless you're told otherwise, which would be rare, always assume that the specific heat of the system is exactly the same as the specific heat of the water. We want to know what the molar heat of dissolution. So this is going to be our delta H of our dissolving reaction. The reaction is going to be, I didn't write it in here, is going to be that the H2SO4 as a gas dissolves to make 2H plus SO4, 2 minus aqueous. So we want to know what the delta H of this reaction is. So we got to work with what we have. The first thing we know is we know the delta T of the water, we know the mass of the water, we know the specific heat. So let's work with that. The mass of the water was 175 grams. The specific heat of the water was the 4.184 joules over gram times degrees C. And the delta T of the water, we had 14.9 degrees C minus 10.0 degrees C. Yeah, I know this is an easy calculation, but let's do it out anyway. Delta T, always label your calculation, 4.9 degrees C. Notice the delta T is positive. Final minus the initial, the delta T, the temperature went up. So 4.9 degrees C. Let's do some canceling here. Grams cancel with grams. Degrees C cancel with degrees C. And that leaves us with, and the last thing we want to do in this case, because we want to have the delta H of the reaction. I know it doesn't say in here, but in the homework we will. We want delta H as always to be in kilojoules per mole of reaction. So we're going to multiply this by 1 kilojoule over 1,000 joules, and I got to squeeze it in here. And if you do the calculation, and you probably should, to sig figs we get 3.68 kilojoules. Now that's just the amount of heat that's being absorbed by the water. Now what we have to do is take that and turn it around. First thing we need to know is, since we're doing per mole of reaction, and the reaction is 1 mole of reaction, and 1 mole has 1 mole of the reactant. The moles of the reactant is going to be the 4.90 grams of our H2SO4, and molar mass, 1 mole of H2SO4. I will spot you the molar mass is 98.09 grams of H2SO4. And cancel out the grams, and we get 0.0500, my mistake, 0.0500 moles of H2SO4. All right, so now we got a kilojoules and we got a moles, but we're not quite there yet, because what we have to realize, as we saw up above, the delta H of the reaction, if we're doing this kilojoules per mole, we do have to take the Q that we measured, and the Q of the reaction is always the negative Q of the solution, or negative Q of the water. So in step number 1 here, we actually measured the Q of the solution, not the Q of the water, but it's really the same thing. And so we can just take that number and put the negative 3.68 kilojoules, and we're going to divide that by 0.0500 moles of the reactant, moles of H2SO4, and that's going to turn into negative 73.8 kilojoules per mole of the reaction. So that's how we get the delta H, the enthalpy change for this reaction. Notice that because it's negative, this is an exothermic reaction. If we had had a negative temperature change in the water, so if the delta T of the water was negative, that would lead to a positive delta H, and that would be endothermic. So If the water temperature goes down, that's going to be your sign for an endothermic reaction, and you will have some of those on the homework tonight. So we can use the change in temperature to find out how much, what the delta H is. We can also turn that around, and we can use the delta H and the energy released to find out what the amount, what the temperature change is going to be for a particular process. So here we have some SO2, and I'm also going to illustrate one more thing in here. SO2 gas reacting with oxygen to make SO3, and the delta H of the reaction is negative 198 kilojoules per mole of reaction. Now that's per mole of the reaction as written. So if I'm going to look at SO2, that's also going to be, oh, sorry about that, for every 2 moles of SO2. So since we have 2 moles of SO2, that's how many moles there are in 1 mole of the reaction. What I want to know, let's change colors here, is how much heat is going to be released. We're going to take 75 grams of SO2 with excess water, ignore the water, and it's going to be absorbed by 2 kilograms of O2, 2 kilograms of water, starting at a temperature of 25 degrees C. What is the final temperature of the water? So again, working with what you know. What do you know? You know the grams of the SO2, and so the grams of the SO2 can get you to moles of SO2, can get you to the kilojoules released, because that's going to be stoichiometry. So Q of the reaction, Q meaning how much heat is released by the reaction. Start with our 75.0 grams of SO2. Let's convert grams to moles. 1 mole of SO2. Again, I'll spot you the mass here, 64.07 grams of SO2. Excuse me, I was about to cough and that screwed up my thinking. SO2. So grams of SO2 cancel out. Now we're going to have negative 190. I want to keep to that negative sign. Negative 198.0 kilojoules for every 2 moles of SO2. So this is where the stoichiometry becomes important. Cancel out the moles of SO2. And if you did the math correctly, you should get negative 116 kilojoules. Notice that that is an exothermic reaction, and that means that that amount of heat is going to be released into the water. Now, let's go back to the water. Notice that we had 2 kilograms of water. Make sure you convert, because the specific heat of water is in grams. You always have to convert to from kilograms to grams. I'm also going to throw a little curveball at you and give you volume on the homework, but I've given you a hint on that, so I'm sure you'll be able to figure it out. So the Q of the water is now equal to, we also need to convert, since specific heat of the water is in joules, the Q of the water is going to be positive. We're going to turn it around. It's going to equal negative Q of the reaction, so positive 116 kilojoules, right? So we need to be negative Q of the reaction, but a negative of a negative is positive. And we need to convert this to joules. So we're going to take 1 times 10 to the third joules in 1 kilojoule. And that's going to turn out to be 116,000 joules. Or you can write 1.16 times 10 to the 5th if you want to do that. All right, so now we've got the Q. So we can take our Q equals MC delta T, rearrange it to solve delta T. Now be careful. Don't try to be fancy and put in T final minus T initial here. If you try to do that, you're going to get all sorts of algebra that you're not going to want to solve. This is going to be the easiest way. Solve for delta T first. Q of the water is positive 116,000 joules. The mass of the water we said was 2,000. I'm going to use sig figs here, 2.00 times 10 to the third grams. And the specific heat was 4.184 joules per gram times degrees C. And we know that the grams cancel with the grams, the joules cancel with the joules, and we have degrees C in the denominator of the denominator. So that comes up to the top and gives us 13.9 degrees C is our delta T. Now notice that's positive, so the temperature goes up. Make sure you pay attention to whether the temperature is going up or going down. And our last step, the final temperature, we rearrange the equation equals the initial temperature, which we said was 25 degrees Celsius, 25.0 for some sig figs. And we're going to add that 13.9 degrees C and get a nice round number. I'm kidding, 38.9 degrees C. That's the final temperature of the water that we've added that heat to. Okay, I hope this lesson has been enlightening, and time for the homework. Good luck, and I will see you next time in class.